Yes, I guess you find.
Of course, yeah. Now I don't have any choice, right? You started that. Okay, yes, and yeah, you can see here. Oh, got it. So I will talk about some work that I did with 3 co-authors. 2 of them are here, and Ray mentioned them, so Paulo and Rita. The third one couldn't actually make it, and it's quite sad. I'm not sure if Emanuele is in the audience. He's not here. Okay, then anyway, but hopefully next time he can also make it. Good, so I am going to talk about a paper that we wrote at the end of last year, basically. And we figured out in the last month that there were some parts that we were simply missing. So we thought it might be good to revisit this and polish it a little bit. And so this part that I'm going to tell you is about this. So it's about principal differential calculi. So what is the main goal? Okay, pointer is not working. Yes, so thanks. Good, so the plan of the talk is the following. So I will work with Hopf algebras and co-module algebras of this Hopf algebra. And the main question that we are going to pose is, given a Hopf extension, B being the invariant elements of this under this co-action of H, can we find some calculi on A and H such that we will have a Hopf extension of graded algebras? So this is what you see here. I will try to use the magic pointer. Wow. Yes. So meaning that the 0 order Hopf amplifies to higher orders. What is needed? Yeah. And so we are going to answer this for the first order differential calculi. And this is what will lead up to the notion of principal differential calculi. What we will need for this is the notion of a principal co-module algebra. This will use something horrible, which is faithfully flatness, but we will find some ways to deal with this horror and to make it somehow more feasible. And then we also have to talk about base forms, horizontal forms, and certain compatibility. And so after this, let's say, affine section, we are going to talk about sheaves, where then locally we are going to have this principal differential calculi properties. Let me also mention that here is some kind of clash of names. So different groups have different names for similar things. So what we call quantum principal bundle is something different than other people call it. So I will try to make it clear what the definitions are. And so let's dive into it. I will start very basic. I guess that most of you, or maybe everybody, knows this slide here. So what is a first order differential calculus? We start with just a algebra A. We don't want to have commutativity. It could be anything, any algebra A, and usually just over a ring K. So you can think of the real or complex numbers or some formal power series or something crazy. I mean, everything is possible. And then a first order differential calculus on this algebra A is this tuple gamma comma D, where gamma is just an A bimodule and D is a linear map satisfying the Leibniz rule. Nothing special. And I just learned that maybe one could even kind of weaken this Leibniz rule and allow for some kind of twisted Leibniz rule. I'm not sure if this is really the right thing. It sounds really creepy, but maybe we're going to try to make this work in the next days. So we will talk about this also, but not in this talk. Here, just Leibniz rule, everything is nice and simple. Huh? Yes, maybe over a beer, that's a good idea. Yeah. And so the second thing that we need is surjectivity, meaning that every one form we want that we can write it as some A, D, B, or some finite sum of these things. examples is just the classical the RAM calculus we know from differential geometry, where the module of one forms is just sections of the cotangent bundle. And I also have some baby example here, just that you can see this is not everything. You can go a little bit more crazy. For example, this you take rational functions in some parameter t, and you take some quantization parameter q, and you say your module of one forms gamma is now just spent from the left. You can multiply with your rational functions, and you have just one form dt basically that you multiply. And you're saying that your right module action is the same as the left module action, but up to this parameter q. So when you move things from the right of a dt to the left, you will get a q. And you can see that the differential corresponding to this is given by this formula here. Yeah, so which goes to the usual differential in the limit q going to 1. Very good. Then, yes, so if you have not only an algebra, but you have a co-module algebra, you can ask for more. So you want your calculus to have more properties. So let's first say, yeah, we are having a Hopf algebra H with a coproduct delta, co-unit epsilon, and antipode S. I guess all of you know what a Hopf algebra is, so I don't say anything about this. And a right co-module algebra is just an algebra with a right H coaction, and this coaction has to be an algebra map. This means co-module algebra. And so this coaction is denoted by delta A. And we are using this shorthand notations. So for delta H, we just write H1 tensor H2. Well, it's clear that this is usually a finite sum, but we are lazy, so we are just writing this. Yeah? And in a similar way for the coaction, but here we are using the 0 to somehow note, okay, this is special, this is the part in A, and the 1 is this part in H. So then a covariant calculus is just a first order differential calculus, such that this map 1 makes sense. So that this is a well-defined map from gamma into gamma tensor H. And just to be clear, usually this will not make sense. So this will usually not be well defined. But if it is, we call it a right H covariant first order differential calculus. To make sense of this map, oh, there's a question. Should I open the chat? Oh, a very long question. Oh, comment. Can we do it later? I mean, it's a long one. Oh, this twisted Leibniz rule. Please ignore me. No, I guess it's very interesting, but okay, maybe I can come to it afterwards. Sorry. Okay. So what this definition means, so is telling us the rationale of this definition is given by the following proposition, which just says that you have a right covariant differential calculus. Should I simply continue? Okay. So okay, so this is saying that you are having a right H covariant first order differential calculus if and only if those two things are valid, namely that you have a right H coaction on gamma that is compatible with the A bimodule action. So then this means that gamma is a right H covariant A bimodule, and this compatibility is written out here. This is this delta on the A acting on the left, A prime acting from the right is just this part here. Yeah, so it's basically bilinear. This is what this means. Yeah, and we also want that D is a right H co-linear map, and okay, it's clear what this means. And if this is the case, then this coaction on gamma is determined by formula 1. Okay, let's go. Move on. Some quite trivial lemma that will be useful is that if we have a right H covariant calculus, on a right-H comodule algebra A, we can get from an algebra injection and from a algebra surjection, we can get other calculi. Yeah, so this is just this is what is written in 1. Simply means that if you have some comodule algebra injection iota from some A prime into A, you will get a second calculus gamma iota, just as the pullback calculus, basically. Yeah? And the differential 2, you simply restrict to the image of this map iota. And this will be a covariant calculus on A prime. And in the same way, you can do this for a surjective map pi. And so here, this quotient calculus will be this quotient you see here, where the kernel is gamma I, which is given by this formula here. So I is the kernel of pi. And so you just have to take care of those two terms. And you can prove this is an A prime pi module. And the differential is given by this formula here. So this is called the quotient calculus. And in case you're having a section of this map pi, you can prove that both calculi that you get are actually isomorphic as covariant first order differential calculi. Okay, this was just a 101 about covariant differential calculi. Nothing special, nothing new. The next thing, also quite basic, is about Hopkar extensions. Here we also start with a right-H comodule algebra, and we are looking at this subalgebra B given by the invariant elements under the coaction of H. So you can see that's written here, all the elements A, that if I act with the coaction on A, just give you a tensor 1. And then we are saying that B inside of A is a Hopkar extension if the following map is a bijective map. And so this map chi, canonical map, is from A tensor B A into A tensor H, and basically just given by the coaction, and then you multiply in A the first two. Some examples of Hopkar is very trivial one when A equals A. When A equals H, sorry, then the subalgebra of invariance is just the ground ring, okay? And you can see that the inverse of the canonical map is basically just given by the antipode S. And you can actually prove that if you have a bialgebra, then this bialgebra is a Hopf algebra, if and only if you can find this inverse of chi. Second fundamental example is a principal G bundle, pi, from P to M, with a G action of a Lie group G. You're looking at the corresponding algebra, which is the functions on the manifold M, and the Hopf algebra is just functions on the Lie group G. And then from this right G action on P, you are getting the corresponding coaction as the pullback map. Yes, so this is a contra-variant functor, so you have to reverse the error basically. Yeah. And here you can see that the space of invariance, so that's the point here, is really just given by the functions on M. Yeah. Okay. Did I make a mistake? I think this has to be P here. Yes, okay, sorry, yeah. Okay, and so also here for a principal G bundle, we are having a canonical map, which is now from P cross G into the fiber product. And you will see that the pullback of this canonical map is just the map chi that we're having in this definition. And you can prove that this is a bijection exactly because R is free and transitive as an action. So this somehow motivates that Hopkar extensions are more general than principal bundles, and we want to think of them as kind of quantum principal bundles. Yeah? but there's something that we are missing, and this missing part, before we can call it a principal bundle, is faithfully flatness. Yeah? So we are making this following definition. Here, for some technical reason, I want K to be a field. So let's K be a field. Then we are saying that a comodule algebra, A, delta A, is a principal comodule algebra if the following two things hold. So if it is a Hopkar extension, and if A is faithfully flat as a left B module. What this means is that we are having a functor from the category of right B modules to the category of relative Hop modules. Those are, so this is this MAH. What this means is those are modules that have a right A action and a right H coaction with, that are compatible in the sense that the coaction is right A linear. Sure.
Usually I would just see this as going into vector spaces. So I mean, if it preserves exactness, then vector spaces are mod HA, it doesn't matter, but reflecting them, because it's a non-full subcategory, so you have fewer morphisms, so you have, is that correct?
So you are saying I should see it as mapping into vector space. I shouldn't consider, I mean, here you are.
Maybe it doesn't make any difference, I don't know.
So here you are getting for free, of course, the right action and the right H coaction, but you are saying, so if I want,
there are fewer morphisms in the category because,
of course,
so then you should, in principle, have fewer exact sequences.
Okay, so it might be possible that maybe for some technical reason it would be better to see it as vector spaces. I'm not sure at this point. As I said,
it doesn't matter so much.
I'm quite new in this field. You are working. You're working with those things for a much longer time, so I'm pretty sure you're right. Yeah, and okay. So then I have to think about this. Yeah, but the thing is, okay, that 2 is quite hard to check because so what this means is that we would have to check for every exact sequence. We have to prove that if we tensor, we still get an exact sequence and also the way back. And so this is something that is usually you cannot do by hand. It's simply not possible. So there are different ways to characterize those faithfully flatness. And so in combination with Hopkar, you can replace this number 2 by 2 prime or 2 double prime, which means so the 2 prime is that you just have to find a section of the left action L of B on A as a map that is left B linear and right H collinear. And so this is much easier to find. Yeah? And the 2 double prime means that you just have to find a kind of cleaving map, but not really a cleaving map. So just a right H collinear unitary map from H to A. And so just maybe to motivate a little bit this definition, so Schneider tells us that if we're having a principal comodule algebra, then the right B modules and the relative Hop modules are equivalent as categories. So that's quite useful theorem. Having a principal comodule algebra, we can talk about base forms and horizontal forms. How does this look like? Let's take just a first order differential calculus on A. It might be a right H covariant one, but we don't really need it. Since we are having the algebra inclusion map of B into A, we can form the pullback calculus. And so we are having a calculus on B, so on the invariant elements of A. And so this we are calling the calculus of base forms. And now we can further build a sub bimodule of horizontal forms that is just given by the left A span of gamma B. Also one technical thing, maybe the two are talking about it. So some people actually take the span of A from the left and the right. So they see horizontal forms as an A bimodule rather than an AB bimodule. I will later try to motivate why we stick to this one. In most cases, it's the same, I would say. Like in most examples, you can actually move a function on A to the left side. So it's not really a big difference, but there is one. Yeah. Horizontal forms, very good. And now there's also something called the vertical map. And it's written here. So for this, we also need a left covariant calculus on the Hopf algebra. Let's call it gamma h dh. And then the vertical map is a map from the calculus on A into the cotensor product of A with the calculus on H. So maybe I just tell you, I first tell you what the cotensor product is. So this is this space here. It's just the dual notion of the tensor product over an algebra. So this just means I'm looking at the sub K module of the tensor product of those elements that if I coact on the first, this is the same as if I coact on the second. And then the vertical map is defined. So I take a form on A, I apply the coaction on A and on A prime, and I apply the differential on A prime 1, which gives me a form on H. And then I multiply it in this way here. So you can see it, this is automatically something in A tensor gamma H, and you can actually prove this automatically lands inside of the cotensor product. The bad news is this map does not have to make sense. So it might be ill-defined. And we have to take care of this problem. So yeah, so this leads up to the definition of what a principal differential calculus is. So now we collect all the things that we talked about. Given a principal comodule algebra and a first order differential calculus on A with a left covariant calculus on H, we call this a weak principal differential calculus. There's some kind of alarm. I hope it's not a bomb or something. Yeah. Yes. Okay. So we call this. Should I?
Here again, saying that people sometimes call these strongly horizontal forms.
Okay.
As opposed to A, gamma, B, A, which are horizontal.
Right. So this is also in Beck's Majid, I guess, right? Yeah. Strongly horizontal forms. Okay. Yes. I'm trying to motivate later on why we call it like this. Okay, so let's come back to this weak differential calculus. So here we are saying we call it like this. If this vertical map actually makes sense, so if it is well defined, and if furthermore we are having a short exact sequence written here. So what does this mean? This means I have an injective map here of A tensor B gamma B into gamma A, and then the vertical map, which has to be a surjective map, yeah? Such that the kernel of the vertical map is the image of this map here, which is exactly by our definition the horizontal forms. So that's also why we choose it to be the left A and not the A bimodule, because then the kernel of the vertical map is exactly the horizontal forms as it should be. Good, and we are calling it furthermore a principal differential calculus if in addition, the calculus on A is a right H covariant one and the one on H is not only left covariant, but even bi-covariant, meaning that we're having a left coaction and a right coaction compatible with the module actions and the differential. So before tackling the examples, I will prove, or not prove, but show you a lemma that in most cases, we will use this lemma to make sure that the vertical map makes sense. Yeah? So this is like an easy tool so that we don't have to prove all the time that the vertical map is well defined. What does this lemma say? So if A is now not only a comodule algebra, but even a Hopf algebra, and we're having a Hopf algebra quotient, then by this previous lemma, we saw that given a left covariant calculus on A, we can get a left covariant calculus on H as the quotient calculus. Yeah? And so this is what this lemma says, basically. So first of all, this delta L means I can see the calculus on A as a left H covariant calculus simply by identifying the left A coaction as a left H coaction. And so then the corresponding quotient calculus on H is a left covariant calculus. And furthermore, the vertical map is well defined because you can prove it is exactly the same as this left A coaction on gamma A concatenated with the calculus projection. So this pi gamma is the map from gamma A into gamma H. You can prove that in this case, this is exactly the vertical map. And so this is well defined. Good. Oh, I cannot. Examples. Okay. Consider the Hopf algebra quotient of OQ as U3 into U1. I don't give the definition of this Hopf algebra now. Later on, we will have SL2, which I will show you, and it's basically the same thing. So just see it as some kind of Q deformation of SU2. And okay, we can see A, which we call SU2, as a right U1 comodule algebra. And you can prove that the corresponding invariant elements are exactly the Potlatch sphere. And furthermore, you can see that this will give you a principal comodule algebra. So now you have a different calculi you can start with on A. So we can test the 3D left covariant calculus on A. And using this lemma that I showed you, this previous lemma, you can actually show this gives you a weak principal differential calculus, meaning you have the short exact sequence. But as we saw in the definition of principal differential calculus, we would actually need a right covariant calculus on A and a bi-covariant calculus on H, while here we are just having a left covariant calculus on A and a left covariant calculus on H. So it's close to it, but it's only fitting the definition of a weak principal differential calculus. You can also test the 4D bi-covariant calculus. This is better in the sense that now you are having a right covariant calculus on A and also a bi-covariant calculus on H, but it turns out the sequence doesn't work. So it's not an exact sequence in the sense that the kernel of the vertical map does not fit the horizontal forms. So this is not working.
There's a question for Ben-Marie in the chat. Ben-Marie, if you want to just unmute and ask.
Yeah, so just a point about, sorry, so just a point about the 3D calculus on SEQ2. You still get a full-on principal differential calculus, but I guess the point is that you're not bicovariant, but you still have this vestigial right U1 covariance on the 3D calculus. So the 3D calculus on SEQ2 isn't bicovariant for SEQ2, but you still have this vestigial right covariance for U1 that makes it all work out.
Okay, so you're saying, so I can still view, okay, I can still view, of course, H as a bicovariant, so the corresponding calculus on H as a bicovariant calculus. And okay, of course, I can transform a left covariant calculus into a right covariant one. So you're saying one could make this into a principal differential calculus in the sense that that we defined.
Yes, but the important thing is that you still have this vestigial extra, like U1 covariance.
Since okay, interesting. So maybe we can make it work. It should be possible. Yeah. Yeah. Okay. Thanks for the comment. Yeah. Then okay, this would even be a full example, even better. Yeah. Thank you. Oh yeah, sure.
It's not exactly what I was speaking yesterday. So it's a right A covariant, left H covariant.
Okay, so it is not a bicovariant corresponding to H, but it's only right A.
Of course, you can make a side covariant.
If you project, yeah. Okay, so you're saying it's even more because okay, I even have it on A, and so I can project, and then I have a bicovariant on it. Okay, no, then this is a full a full principal differential calculus. Great, thanks. Good. Okay, Another example we could have is the smash product calculus. Yeah. So I will just go through this quickly. It's also something quite basic but interesting. So given a left H module algebra, so this means you are having now not a coaction, but you're having a left H action on an algebra B. Then you can build a smash product, which we denote by this B smash H. And you can prove this is a right H comodule algebra, with coaction just being the coproduct on H, and with algebra structure written here. So we have this multiplication here, where you can think of, I multiply this, I simply put all of the B's on one side and all of the H's on one side. But this H has to pass through B prime, so that's why H somehow has to act on B prime. And yeah, so you can prove this is an associative unital algebra. And corresponding to this coaction that I just mentioned, this is even a right H comodule algebra. There's a canonical first order differential calculus. Okay, if we choose first one on H. Okay, so choose any bicovariant first order differential calculus on H and take an H module first order differential calculus on B, meaning this is a first order differential calculus with a left H action compatible with the differential, in the sense that I wrote. So if I act on an exact form, this has to be like, okay, I can simply act on B. In this case, if I have this data, there's a natural covariant calculus on the smash product. And this is this smash product calculus defined by Pflaum and Schaumburg. And yeah, it is given by this direct sum, with the first one just being gamma B tensor H, but with a different module action. And this module action is somehow mimicking this smashed multiplication. Now just using also the H action on gamma B. And that's why I'm writing here gamma B smash H. And in a similar way for the second one, so for B smash H, it's also just the tensor product with a different module action.
Got another question in the peanut gallery. Go ahead, Brenner.
Sorry, legacy hand, as they say.
Okay. Okay. No, it's actually good that he's asking questions. I like it. Okay, and so the differential is just the sum of the two differentials we are having on these calculi. And you can prove this is not only a right H covariant calculus, but even a principal differential calculus. So you see that you have the exactness of the sequences, of this sequence, sorry. Okay. Okay, another question? Okay, very good. Yeah. Good. So now here, this next slide is a little bit to motivate this definition of principal differential calculus. What is this good for? Yeah. And so you know that the main goal of the talk was somehow to get a graded Hopkar extension from this definition. And so here we, I try to show you how this works. Yeah. So given a principal comodule algebra and a principal differential calculus, we have the following lemma. So we can, of course, see this omega h as a graded Hopf algebra. Okay, how does this work? So this is a direct sum where we are just looking at the zero order, so just functions basically, and one forms, so the h plus gamma h. And we can see this as a graded algebra by simply, okay, you know how to multiply. And if we multiply two one forms, we simply get zero. Yeah? And there's also a coaction, which in order 0 is just the coaction on h. And in order 1 is given by this sum of the left h coaction on gamma h and right h coaction on gamma h. So you see this is a map from gamma h into, the first one is gamma h tensor h, and the second one h tensor gamma h. So right and left coaction and the sum of this one. You can prove this is really a co-algebra, and even more, this gives you a a graded bi-algebra. And you can do the similar things for the antipode, where now this is using both of the left and right coaction in this way here. So this gives you a graded Hopf algebra. And this only works because we're having a bi-covariant calculus on H. This is really telling us if you want a graded Hopf algebra, we need a bi-covariant calculus on H. Furthermore, we can see this A plus gamma A as a graded comodule algebra corresponding to this Hopf algebra, this graded Hopf algebra. And so the coaction in order 1 is now the sum of the coaction, of the right coaction we are having by assumption on gamma A plus the vertical map. So this is where the vertical map appears. So let's check that this makes sense. So the first one here is a map from, okay, it doesn't make sense because I didn't write it correctly. It should be from gamma A into this here. So this is missing. From gamma A into gamma A tensor H plus A tensor gamma H. The first one being the right H coaction on gamma A, the second one being the vertical map. So actually here would be the cotangent product, but okay, we don't mind. And so the theorem would be, if we have a principal differential calculus, then what we have here is really a Hopf-Galois extension of graded objects. Yeah. And I should mention that this we are massively using a paper of Schauenburg from '96, where he is talking not about this in the differential graded setting, but in the graded setting. So he's somehow classifying graded Hopf-Galois extensions, and this is where those sequences appeared. Yeah? So this is somehow what is needed to make this work. And what follows from this theorem is also a nice classification of base forms, which is telling us that base forms are exactly the intersection of invariant forms with horizontal forms. Also something we know from classical differential geometry, but we could not prove in the general setting. So this really needs this notion of principal differential calculi. Otherwise, you just have an inclusion of gamma B into this intersection. Sure.
Does this still holds when you pass to the prolongation of the first order differential calculi? Do you get a grade? You don't know. Okay.
So in general, I would say no. There you need like higher sequences. What could be the case? So since the for a higher order differential calculus, this is determined somehow in degree 0 and 1, there might be a chance that this could work in some cases. But in general, so Schauenburg tells us you need, for every order, you need one of those sequences.
Ah, okay, thank you. Thank you.
But yeah, that's definitely also something we want to check if in this differential calculus case, we can make this work even for higher orders, only using this one sequence and not like infinitely many ones. It doesn't work if you, right, yeah. So yeah, even just proving that you get a comodule algebra might fail. Yeah, so yeah, you can see you would need somehow more higher order vertical maps. Yeah. Yeah, but it's definitely something I would like to see if one can make this work, or what is needed to make this work. Yeah. Okay. Great. Okay, so now we are coming to the sheaf part. 15 minutes left. Okay, great. So let's see. So here I will tell you something about the first paper, or a paper of my co-authors of last year, where they introduced the notion of quantum principal bundle, where this now does not mean what other people mean by quantum principal bundle, but this means the following. So motivation. So if you have a surjective morphism of algebraic varieties, P an affine group and an associated Hopf algebra H, then by a theorem of Pflaum, you know that the notion of a P principal bundle is the same as having a sheaf F on M, defined in the following way as the functions on the pre-image of the projection map. So if and only this gives you a sheaf of right H comodule algebras such that you have some local properties. And the local properties on an open cover, they're specified there, are the following, namely that the invariants of this sheaf locally are isomorphic to the functions on the base. And secondly, that you have this splitting here. So this is an isomorphism of right H comodules, not of algebras. Yeah. And yeah, so this classifies P principal bundle in a sheaf theoretic way. And condition 2 basically just says that you have a cleft Hopf-Galois extension, meaning this is a special kind of Hopf-Galois where you actually have more. You have this convolution invertible right H collinear map J, which is called a cleaving map. Yeah, and then what my co-authors did was taking this theorem and making it into a definition in the quantum realm. Yeah, saying so now take any sheaf F of right H comodule algebras, and you call this a locally cleft quantum principal bundle over M if on an open cover you have those properties 1 and 2. And for 2, we even allow for a general Hopf-Galois. So this does not have to be this cleft. We can even allow any Hopf-Galois locally. Okay. Maybe since we're running late, I skipped this part, or okay, let's make it quick. So so actually that's quite crucial. So I should say it at least. Okay, so the main examples that we will have of this quantum principal bundles are of this type. Take G, a complex semi-simple algebraic group, and P, a parabolic subgroup. Then you can look at G mod P as this, yeah, you can look at the corresponding principal bundle. You're having G here going to G mod P. And so now take any Hopf algebra quantizations of the corresponding functions. Then what we need for the following theorem is the notion of a quantum section. That's a little bit technical. Let me just maybe say briefly. So this quantum section is somehow needed to determine the algebra on the base, on G mod P. And also, furthermore, this quantum section gives you an open cover of M in this way. So this is some element of OQG that when you act with the coproduct, you will have this kind of sum here over I. And if you take the elements on the right side, they will determine this open cover UI. You will see it in the example of SL2. You will see clearly what it actually means. Yeah. Given this open cover, we can now find a topological basis of M in this way. We are just looking at all finite intersections. I mean, they're always finite since we're having a finite open cover. So this will always be a finite intersections. And this will give us a topological basis. And then what my co-authors did was proving this theorem that, yeah, starting with this Hopf algebra quantizations, you can build a sheaf, actually 2 sheaves. So the first one here, OM, is a sheaf on the base. And this works in this way. So given any open of the topological basis, you define this thing here. And it looks a little bit complicated, but it's basically just combinations of these elements of the quantum section, yeah, where you allow the first one, so the I11, to be invertible. Yeah, so those are the OR extensions of this CQ. Yeah, and you can prove that this gives you a sheaf of algebras on M. Furthermore, you can get a sheaf FG if you OR extend OQG, also using these quantum sections. Yeah, and it's kind of nice because what you get is that So those two sheaves, they are not just random things, they talk to each other in the sense that the invariance corresponding to the coaction of the parabolic is exactly given by this base sheaf, locally. So you can see for any open of this open cover, you see that the invariants are exactly this elements of the base sheaf. So maybe let's look at an example of SL2. So SL2 is the free algebra generated by some elements alpha, beta, gamma, delta, and then you have some commutation relations that are listed here. Basically, if you flip 2, you will get some q minus 1. In most cases, not for beta and gamma, they like each other. Alpha and delta really hate each other. So here you have a very complicated commutation relation. And this last one is just the quantum determinant relation you have here. Yeah? So here we can define a second Hopf algebra, which is generated by some t minus 1 and p, where we quotient now just by the commutation relation of t with p gives you a q minus 1. And this can be seen as a Hopf algebra deformation of the parabolic subgroup of SL2. And those are actually Hopf algebras in the sense that this delta here gives you a coproduct. And I didn't write down the antipode, but it's also not complicated. And furthermore, we are in this previous setting. So we are having a Hopf algebra projection simply by mapping alpha, beta, gamma, delta into t, p0, t minus 1. Good. And so let's build a sheaf out of this example. So we want to see this as a sheaf over CP1 or P1C. You can also write it like this. So here we will take a very simple open cover. We just take the upper hemisphere and the lower hemisphere. This is U1 and U2. And then the only opens we are having here are the empty set U1, U2, the intersection of U1 and U2, and the total space. Of course, this is very coarse. This is, you might say, why should we work with this thing? This is telling us nothing, but it's not true. It's actually enough for this example to give us something interesting in the quantum setting. Classically, of course, you want to use something finer, but here it's somehow giving us all the information that we need to somehow understand quantum SL2. So the corresponding sheaf is given like this. On the empty set, we simply take the 0 algebra. On the upper hemisphere, we take the OR extension, where we allow alpha to be an invertible function. On the lower hemisphere, we allow gamma to be invertible, and on the intersection, both, so alpha and gamma. And on the whole space, we take all of SL2. And okay. Yes, so this is the let's say, sheaf on the total space. We also have a sheaf on the base. This is this O P1C. And so here we define on the upper hemisphere, we are looking at all the, so the polynomial algebra given by just one generator U, where U is alpha minus 1 gamma. On the lower hemisphere, we take the inverse of this one, so gamma minus 1 alpha, which we call V. And on the intersection, we take both, so U and U minus 1. And as we know, globally on CP1, there are no non-trivial functions. So those are just the constant ones. So this is and this is actually the reason why we need this sheaf approach, because globally we don't see much. Globally, we have just the constant functions, and this example is kind of void. We really need this local data to make sense of SL2 here. And okay, the only non-trivial restriction morphism that I have to show you is the one from the open U12. No, sorry, from the open 2 into U12. And this maps V into U minus 1. And since I'm running out of time, I don't tell you. So you have some cleaving maps here, but okay. And okay. So this was known, and so this is how to get this sheaf of algebras. Now we want to do the same thing on the differential calculus level. So we want to make sense of an OR extension of differential calculi. And so just very briefly how this works. So if you have an OR element A in your algebra A, you can define, given a first order differential calculus on A, you can extend this to a first order differential calculus on the OR extension in this way here. So you basically take gamma, but you tensorize on the left and on the right with this OR extended algebra. Okay, this is clearly a bimodule corresponding to a minus one trivially, yeah. The differential here is given like this. You take the usual differential if you take functions on A, but if you take a minus one, you take this kind of strange formula here, but this is just needed to make the Leibniz rule work. So if you write it down, this is exactly forcing the Leibniz rule for this inverse functions. And you can prove this gives you a first order differential calculus on the OR extension. And if you have a coaction, everything is fine, and you are getting a right age covariant first order differential calculus. So now, since we have the definition of sheaf of comodular algebras, so here we also need a definition of sheaves of covariant first order differential calculi. And this is just mimicking what we did on the algebraic level. So we are saying, giving a sheaf F of comodular algebras, we call a sheaf cactus. I mean, it really looks like a cactus, that's why I call it a cactus. A sheaf of F by modules. We call this a right age covariant calculus. If there's a morphism of sheaves of H comodules, from F to gamma, such that we have some local properties. And the local properties are, as you would guess, just the Leibniz rule and surjectivity. So this 1 and 2. And okay, we're proving like the analog theorem that we had on the algebra level, also for first order differential calculi here, meaning if we start with a covariant calculus globally, so let this here be a covariant calculus on the Hopf algebra of OQG, then by the previous theorem, we have this sheaf FG, and we proved that we can extend, so via OR, we can extend this calculus to a sheaf of FG. And that's basically what's written here. And that's in a nice way that the corresponding calculus on the base functions is just the pullback calculus corresponding to the algebra embedding here. Okay, like 4 minutes, very good. And so now it's very natural to say this is even, so this sheaf of calculi, or this calculi or the sheaf, as you want, we call even a weak principal differential calculus, as if we had, just as we had previously, locally we have more information, namely that this vertical map makes sense and we have an exact sequence, and this we are asking on all opens of the topological basis. And we are calling this even a principal differential calculus if now locally we have a right age covariant calculus and a bicovariant calculus. And then you can basically prove the same things. So it is enough to know this locally that you will now get an equality of sheaves. So having a principal differential calculus means that now you know that your base forms are now, so the sheaf of base forms is now given as the intersection of the invariant ones with the horizontal ones. And almost okay, I think for the examples, yeah, so basically, maybe I can do this one, yeah, maybe I can do GL2. I can do GL2. Okay, so start globally with OQ GL2. So this gives you, via the previous theorem, a sheaf of comodular algebras, which is even written here. So we again see this as a sheaf over CP1. So we have like the two opens U1 and here, okay, this should be U2. Sorry, that's a typo, yeah. We do it basically in the same way. And we also do the OR extension of the bi-covariant calculus on gamma A. And then it turns out that this is really a principal differential calculus in the previous sense. And let me also mention, it is not, so locally, it's not simply the smash product calculus, it's something more complicated. And so maybe just the steps that you can see how this works, and then I finish exactly on time. Yeah? So the calculus on A is a 4D calculus. So we have 4 base forms, omega 1 to omega 4. On the quotient calculus, you see that one of those base forms will vanish, namely omega 2, and you're left with 3 linearly independent forms on this quotient here, omega 1, 3, 4. On the base, so on the invariance, you will see you're getting a 1D calculus generated by just one form that you can calculate. So this D1 of this element U is basically the span of omega 2. And this is good because omega 2 was the form that was vanishing. Yeah. So you can see that now if you look at the vertical map, yeah, you can prove it's basically given by this sum here. And so here you can automatically see that the kernel of this map are just everything that you multiply from the left. So all the forms that are omega 2, and I multiply something on the left with A. So you can see this has the correct kernel. And okay, you have to prove some things, but you can prove this is really exact. You're getting a right covariant calculus on A and a bicovariant calculus on H. So this is a principal differential calculus sheaf according to our definition. So here are some references, and I think that's what I want to say. Thank you.
Sure. I mean, unless there's someone in the room. So let me just begin with my comment at the very beginning. So you're talking about the possibility of maybe considering Leibniz rules. So I have a warning to give from someone from spectral triple land. Like, at least in spectral triple land, the only compelling reason to so if you go back to that very first slide with those basic examples of differential calculi, that example of the Q-deformed calculus on U1 is sort of like the quintessential example of why on the algebraic level you could argue that you don't need to care about twisted Leibniz rules, because the moment you have a twisted Leibniz rule, you just twist the bimodule structure and presto changeo, you have an honest Leibniz rule. The only sort of context where this matters, at least from what I've seen coming from spectral triple land, is in spectral triple land, you care about having a representing one forms by bounded operators. And something like that calculus for Q, a positive real number not equal to 1, you're not going to be able to represent that that bimodule of one forms by bounded operators, and particularly you're not going to have a bounded commutator representation of that calculus coming from something like a spectral triple. So then the game that one might try to play is, okay, we'll use a twisted spectral triple which allows a twisted bounded commutator, a bounded twisted commutator representation of like a sort of twisted first order calculus involving a twisted Leibniz rule. So from that perspective, like when I would say that you don't need to worry too much about twisted Leibniz rules, because that just comes down to fudging the bimodule structure.
Thank you for the comment. I'm not sure if this is true, since there are some, I would say, rather isolated papers which worry about this twisted Leibniz rule, and I'm not sure if you can really always simply compensate this by changing the bimodule structure. If this would be possible, then I mean those papers would be pretty void, right? So I'm not sure. Maybe you're absolutely right, and this is the case. But yeah, I mean,
it depends on what you want to do. I mean, if it's just a single, if you just have a single type of Leibniz rule, a twisted Leibniz rule, which is the single automorphism, then you just twist the bimodule structure and everything's fine. But if you have multiple Leibniz rules involving multiple sort of twisting automorphism, and also if you're concerned about having a like some sort of bounded representation of your one forms, then you have to worry about these things. So that's just that perspective, that idea fix, I guess. Another thing, this notion of a weak principal calculus is actually pretty interesting, because like if you're thinking about something like an SEQ2 principal SEQ2 bundle, like a sort of Q-deformed quaternionic Hopf vibration, like I gather that no one really wants to work with the 4D calculus on SEQ2. And I guess this would open up the possibility of thinking of S7Q as a weak principal differential calculus with respect to the 3D calculus on SEQ2. So I don't know, has that been worked out?
Yes, so that's actually the reason why we came up with this weaker notion, because we found that some of the examples were actually of this type, that we had those sequences that are really useful, but we cannot build this graded Hopf Galois, since we are not able to have this graded Hopf algebra and graded comodule algebra, but still we are somehow close to it. So even if you don't have the graded Hopf Galois, maybe you are still happy that you have somehow the right notion of horizontal forms. And so we thought it was still reasonable to have this weaker notion.
Okay. No, is the Q-deformed quaternionic Hopf vibration, like, is that sort of construction going to appear anywhere, or has it appeared anywhere?
Sorry, can you say it?
So that construction of the S7, like the Q-deformed quaternionic Hopf vibration, in this language, has that been written up anywhere?
I don't think so.
Because that will probably be an example of considerable interest, because it's such a natural thing to want to play around with, and it's.
Okay, so yeah, if this is one more example, then of course would be happy to also have it in the paper, maybe. Yeah. So.
So maybe one more question and then a bibliographical comment. So have you been thinking about principal connections in this regard?
Of course, this would be the next step.
Okay.
Because if you now have a splitting of this sequence, yeah, then of course you really have a direct sum decomposition of your forms into horizontal and vertical forms.
Yep.
And so of course this would be the next natural step. But we figured out that only having this is already a lot, so we keep it for future paper.
So that brings me to my bibliographical comment, and I speak of this from difficult personal experience, since I've been thinking about some of these things in a very restrictive setting of Hofstar algebras, blah, 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 really sort of strict principal differential calculi with the strong blah, 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 blah. So there's a paper from the 90s by Đurđević that got published in 97 that has a lot of formal aspects he figured out quite presciently. He never goes as far as the result like you have, which is, I think, a wonderful thing, that like this clear statement that at least up to degree 1, through degree 1, you have an honest, Hopf-Galois extension of differential graded algebras. He doesn't go that far, but in terms of general sort of formal sort of insights, there's a lot there that one can mine, and then these will become important, especially when you consider principal connections and factorization of calculi into vertical and horizontal pieces. So I had I wrote a rather illegible preprint last summer in a bit of a fugue state, if I may be so grotesquely shameless as to put that in the chat. It's illegible. I'll have a lot of rewriting to do, but I tried to work on differential calculi through degree 2 and principal connections. And so there may be things that you can mind there. But one of the things that sort of, where did I want to go with this nonsense? One of the things that to keep an eye out for is that once you move. So Đurđević's paper has, presciently identifies a lot of the issues, and you'll want to sort of pay attention to what he says, but be forewarned that his notation he has an idiosyncratic take on Voronović's notation, so it can be a bit rough to read until you're used to it. But maybe the one thing to bear in mind is that one thing that becomes apparent when you move to degree 2 is that there's and allow for the possibility of principal calculi, is that there's an intimate relationship between the curvature and what differential calculus you're allowed in the structure quantum group.
Okay, so I will definitely check out your paper and read it. And yes, so for the higher orders, I think it will be really interesting to try to see what comes out of these higher sequences. So if we can really find, as you say, maybe some curvature terms or something interesting in higher orders. And
I'm currently working on a pretty comprehensive write-up. I mean, the CF, the talk I gave in this seminar a month or whatever it was ago, of just a circle bundle case. But if you had to triage, forget my preprint, look at Djordjevic's paper, at least for the bibliographical sort of requirements. So there's formal insights there written up in idiosyncratic notation, but he already is thinking about like having a coaction of the DGA, or et cetera, et cetera, et cetera. So that's sort of out there. Anyhow, let me shut up. This is really cool stuff. So thank you for the talk.
Thank you very much for your comments. I really appreciate. Thank you.
Okay, so any more questions?
The audience?
Yeah, Bogdanimer, about the twisted Leibniz rule, you should think probably it as a about twisted Leibniz rules on the quantum group, you could probably think it from the perspective of a spectral triple on homogeneous spaces, because look like this twisted Leibniz rule should be just a tool to get a proper calculus downstairs on the basis of your homogeneous space.
Yeah, the problem with even with SEQ2 over Podlish, and that's something that I've been thinking through. Things go even worse there, because if you wanted to use twistings to get bounded commutators, like, and this is what we were talking about during my talk. Sorry, Thomas, for hijacking things. You're going to have different powers of Q in the horizontal and vertical directions. You can't even get an on like there is no like I think there's a PhD thesis of a PhD student of Adam Rennie's called Roger Senior, and he wrote up some of this stuff in papers, including one with Jens Cod, where you can kind of sort of get some sort of twisted spectral triple in SEQ2 that kind of sort of works. But the problem is, if you really want to think about the Q monopole and correctly encode the actual, not just the Q deformed complex Hall vibration, but that with the Q monopole and the whole sort of ensemble of differential structure, you cannot do that in the setting of spectral triples, not even of twisted spectral triples, because you have different powers of Q appearing in the vertical and horizontal directions. If you like, you have powers of Q appearing in the horizontal direction because of the generalized braiding on the Q monopole calculi, on the Q monopole connections. But then because of the Q squared and of the curvature, the Q squared of the calculus on the structure group that you're forced to take, you necessarily have Q squared in the vertical direction, or powers of Q squared instead.
What happened downstairs on the level?
Oh, downstairs everything's fine. Yeah. Everything is happening when you go upstairs.
Okay, yes, that's probably like what I was trying to say, that like if at least it's fine on the homogeneous space, then I'm happy.
Yeah, no, sorry, I misunderstood you. Downstairs, you have a fighting chance of being fine, I think, but you folks would know best.
Okay, well, probably we should discuss it once at Podstarom Krovem. Thanks.
Now I'll ask a quick question about the ORA extension. Looked quite interesting for this. So what do you get when you take you're going, let's say for Podlish, you're going to get some differential calculus over the quantum plane, I guess, no? Or maybe you already said that and I missed it. because I mean, you're localizing over a point, so you're going to go to a plane, you get a calculus over the plane. Quadratic is very canonical, so then the most canonical one would be the usual Q-deformed calculus on the plane, the quantum plane, I would guess.
So I'm not sure because, so of course, we were not working with SU2. No, we were working here with SL2, and so here what we are getting, on the base is really the line. So you can see that on the opens we are just having the CQU and CQV. So we are some one-dimensional. Yes. So we are not really getting the Portland sphere. So I'm not sure how you could.
Well, then if you go up, I mean, could you go back to the definition of the? Maybe
just one more thing. Yeah. The point is that globally, so of course in the affine case where you have SU2 and you would get globally the Portland sphere, you could think about localizing, but here the point is that since we are working here over CP1, so globally we have just a constant function. So here there is no Portland sphere. So I'm not sure how to get this.
So if you go up to, I don't know, CP2, for example, then you'll get the plane.
Okay.
But could you go back just to the definition of this? CP2, then you're probably going to get the same thing for the quantum plane, basically. Probably. Yeah. And then the question would be like, for all of these, generally for the flags for these quantum Brouhat decompositions that you have, you can localize over these things, and you would get calculi over the localizations, which would be interesting.
This slide that I were not able to show you. So here, this is just what Paulo said. So this is exactly this. If you move U from right to left, you're getting this Q squared here on the first open, and on the second, you're getting a Q -1. So that's exactly the Q line. Yeah. And as you said, maybe if we go one step higher, you would get the Q deformed plane. I guess this is what we expect. Yeah. You missed it since I didn't tell you, so it's quite natural that you missed it. Yeah. Okay. Sorry. Your second question was.
That basically, then if you go up to higher flags or more general flags, then I mean, when you're localizing over points, I guess this is maybe where Rita would know the classical picture better than I do, but you have these various Brouhat cells and so on. You have Schubert cells, that you're going to go. So localizing over those would be interesting to see what sort of calculi you got over these things. No, it's a very interesting idea, that if you take this Ore localization, then you got calculi.
Yes.
Because then this is really. The Schubert cells and some calculus over them. I don't know, just some sort of an idea, but it's going to be hard, but no, it's a very interesting idea to be able to take the calculus up to the localization.
Yeah, just this for calculus is due to Rita, so it's this is perfect. Yeah.
Okay, so are there any more questions?
Yeah, actually, about the sheaf stuff, has this sort of sheaf theoretic picture been like, can it be applied to examples arising from sort of theta deformation, something like theta, S3 theta over the classical 2 sphere, or something like just irrational rotation algebra over the circle, or like I'm like, I have no idea how to think about something like the irrational, non-commutative 2 torus as being formed from a sheaf over the classical torus or something like that. But has anything been done can anything be done in this sort of direction?
If anything can be done, this I'm not sure. I think we tried to do the torus, right? We started, but we didn't really get far. Paulo, maybe as a comment on this, yeah.
Yes. So a shift description of without a differential calculus is definitely doable, and for example, has been studied with Chiara Pagani and Pierre Bielawski and Alex Schenkel in some paper 4 years ago, exactly for the theta instanton bundle.
Okay.
And now you can ask, can one does the differential calculus there and the deconstruction like Thomas has been showing? Well, it's not strictly necessary, since they are being in an affine geometric algebraic setting, you can work with the sheaf of total functions. But you can, of sections. So you, but it's doable. It's doable, and actually, in part with again Gianni Landi and Chiara Pagani, we are around that point.
Okay, cool. Thank you.
Thank you to you.
So for calculating the spectrum of differential operators, in particular Dirac operators over, CPN or flags in general, is extremely difficult. And classically, I guess what we're really interested in is that the spectrum is going to go to infinity. Classically, you would prove these things locally and then glue them together, but of course, non-commutatively, we don't have any locality. But now you're talking about locality. So then the question would be, if you could, through these breaking things up into sheaves or into localizations, if you could somehow in the, like the quantum planes or the higher ones or whatever they are, you could actually prove things like that by some abstract means that your spectrum is going to go to infinity, and then glue it all together, and you'd never actually have to calculate explicit spectra. So that would be something.
Of course, very interesting.
Yeah.
And yeah, I mean, one of the reasons for this sheaf approach was that, as you said, that usually you don't have this notion of local functions, local sections, and via this sheaf you somehow impose it. Yeah, and of course, then trying to prove some local to global theorems could be really cool. I mean, I would definitely like to think about that. The only problem that I could see is that our topological basis, or the topological space that we are using, is very, very coarse. Yeah, so we don't have many opens. So I don't know if this is really fine enough to get a lot of properties. Maybe it's really too coarse, and
it covers.
It covers, but I don't know. So this is just one comment that this could be a problem, but maybe it's not. It's just something that comes to my mind.
So any more questions?
Comments? No. If not, then I think we'll thank the speaker again. So.
It's, where did it go? Sorry, stop. Yes. So here is Tuesday's talk, Bente from our very own institute. So it will be in this room at 4 o'clock Tuesday. Hope to see you there.